Okay, so let's just talk about what a differential equation is again. Here we have dy on dx, so that's the rate of change of y with regards to x, and it's equal to 2 times the x value squared times the y value. So it's talking about how the slope, the steepness of the relation, okay, not function here, the relation is related to x and y values. So that's a differential equation, that's what it is. The slope is related to the x and y values in this limit. Now this is going to be separable. It's going to be separable, which means we can isolate the x part and the y part. So we're going to start by dividing both sides by y. So I'm going to have 1 on y multiplied by dy on dx is equal to 2x squared.
Could that just not be d over dx?
So
We want y times d over dx, not just...
no, we need a d. Yeah, we'll get there. We'll get there. Okay, so that's our first step. We just move the y term over. Now we're going to integrate both sides with respect to x. So we'll have 1 on y dy on dx with regards to x equals the integral of 2x squared with regards to x. So now our dx's over here are cancelling, and we have the integral of 1 on y with regards to y. This becomes ln of the modulus of y. And on the right hand side, the integral of x squared is x to the 3 on 3. So we'll have 2 on 3, x to the 3. And plus c just needs to go on one side, all right? Because we can collect the constants, whatever they are, we can add them together. Now we're going to solve through here for y. We're going to isolate y. We get y by itself. So we're going to apply e to the power of both sides. So I'll write that out first. I'm going to do it over a series of steps here, right? 2 on 3, x to the 3 plus c. Now, e to the ln modulus of y, we'll simplify that in 2 steps as well. Firstly, that's just going to simplify to modulus of y. And over here, I'm going to split these two terms up. I've got e to the c multiplied by e to the 2 on 3, x to the 3. So that's just the reverse of our first index law that we learned. If we have a to the m plus n, well that's equal to a to the m times a to the n. So we're splitting up that power. Now modulus of y, that just means plus or minus, doesn't it? So we have modulus of y, the definition of modulus is it's positive or negative of this component. E to the c, and then we have e to the 2 on 3, x to the 3. And then what we're going to do is we're going to introduce a new variable just for the sake of simplicity, a e to the 2 on 3, x to the 3, where a equals plus or minus e to the c. So sorry there's not quite enough room there, just because we've probably done more steps than we need to, just to really draw out what's going on. So, what have we done? We started with this differential equation, this relationship between the slope in x and y, and we've isolated y. And so functions of this form, all functions of this form, doesn't matter what that number is out the front, that constant term, okay, that's going to be the relationship between the slope and the x and the y value. Okay. On to b, same sort of thing, we're going to isolate the y component. So I'm going to divide both sides straight away by 3y plus 2. So we'll have 1 on 3y plus 2, dy on dx equals x squared take 4. Then we'll integrate both sides with respect to x. All right, here we're going to have, we've got 1 on ax plus b with ay plus b with regards to y. So this is going to be 1 on 3 ln modulus of 3y plus 2. And over here we're going to have x to the 3 on 3, take 4x plus c. And then the deal is pretty much the same, follows through pretty much the same. There's just a few more operations for us to perform. So first we'll get rid of the 1 on 3 by multiplying both sides by 3. This is going to give us x to the 3, take 12x plus c We don't need to change the c value because it's just some constant, okay? We don't know what the number is, but because we haven't defined it yet, we don't need to say, oh, we've got 3 lots of c. It's just some number there. All right, so we multiplied both sides by 3. Now we'll e both sides, so put e to the power of both sides, and we'll be left with 3y plus 2 modulus here. I might do that step in one go. So I'm putting e to the power of both sides and applying the modulus. Okay. Now what we'll do is isolate the a term. So 3y plus 2 is a e x to the 3 take 12x, because a equals plus or minus e to the c. So I'm splitting up that. I'm leaving that part with that one. That's going to be e to the c. Do you want me to do that over more steps, or is that okay? What do you reckon? Makes a bit of sense, Haley? Okay, yep, Jack. Very happy to write up. Okay. Cool, and then it's a linear equation for y. So we'll take 2 from both sides. And then divide both sides by 3. Now, even then, maybe I was a bit premature in defining a up here, because we could define a down here once we've processed it a little bit more, but it doesn't matter. All equations of that form are going to have that relation. Okay? If this is the differential equation, this is the relation that relates the variables x and y. All right, let's keep going. So they're probably with 2 tricky ones. C and D are probably a little bit easier, less involved, but the process is the same. So we have dy on dx equals x to the 3 on y squared. Let's start by multiplying both sides by y squared. Then we'll integrate both sides with respect to x. Alright, so we get y to the 3 on 3 equals x to the 4 on 4 plus c. Multiply both sides by 3. And then cube root both sides. Maybe I'll just emphasize that point again rather than leaping over that. What we're doing here, if we want to get y by itself, what we're technically doing is putting both sides to the power of a third. Remember, you can do anything you want as long as you do it to both sides of the equation. So if I put both sides to the power of a third, that's the cubed root. Well, over here we've got 3 times a third. And so the left-hand side simplifies to y, and the right-hand side is just the cubed root on that side. So we can express it with the power, or we can express it as the radical. X to the 4 plus c, where c is some constant. Okay, so that's c. Let's move on to d. So d, we have y dash. Now y dash, we're going to use multiple types of notation. That just means the derivative of y, it means the same as dy on dx, is equal to cos squared of x on top of the square root of y. So we'll multiply both sides by the square root of y. So we'll have y to the half on the left-hand side, and we have cos squared of x on the right-hand side. Now already, I'm going to do it at this step because I'm anticipating we're going to be integrating, right? We're going to be integrating the cos squared of x function, and to integrate cos of x, we have to do a double angle substitution. And so what we have, one of our formulas that we've got in our integration summary at 7b is cos squared of x is equal to half plus 2x. Okay, that's the double angle identity where we can substitute cos squared of x for that. And now we can't integrate the left-hand side, but we do know how to integrate the right-hand side using methods techniques. So we're fine to integrate that. So I'm going to perform that substitution here because I'm already anticipating we're going to integrate both sides with regards to x. Okay, and then we're at y. Integral of y to the half is going to be y to the half plus 1 on top of half plus 1. That's 3 on 2 on top of 3 on 2. And on the right hand side we have half x, and we've got half times the integral of cos 2x, 1 on 2 sine 2x, and then plus c. Okay, and just solving through for y now. So this 3 on 2, like a good way to think about that, we've got divided by 3 on 2. That will simplify on this side to 2 on 3. And so then what we want to do is multiply first, multiply both sides by 3 on 2, because that will allow this number out front to cancel. So I'm going to multiply this whole expression by 3 on 2. So we'll have 3 on 4x. Here we've got half times half. So that's 1 on 4. And then 1 on 4 times 3 on 2 is going to be 3 on 8 sine 2x, and then plus c. It's a number, we haven't defined it yet, so we'll just leave it as plus c for now. So that's y to the power of 3 on 2. And just like before, to get y by itself, we're going to raise both sides to the power of 2 on 3. Okay? And 3 on 2 times 2 on 3, that will cancel. We'll be left with y on the left-hand side, and on the right-hand side, we've got this tiny expression where c is some number. So there we go, relationship between the differential equation, and we've isolated the y component, separated. All right, on to 2. Now we have a show that. Now, anytime there's a show that, I don't want anyone to lose marks for a show that. So we have 4. I'm not talking about the one in the last test. There was a tricky one in the last test. Talking about this kind of one, show that this is equal to this. And so what we should definitely do is just make sure you're not skipping any steps, okay? Because if you assume too much, like if you just state that, you haven't shown anything. Anytime there's a show, it means really show, draw out all of those steps that are involved. So we start with, how do we communicate? Let's start with the right hand side. That's what we're going to manipulate. That's what we're going to mess around with. So we state what the right hand side is. Okay. Then we're going to cross multiply the denominators. So what happens when we cross multiply the denominators? We're left with x plus 2, take away x take 2. And now they have the same denominator, x take 2 times x plus 2. And when you evaluate that, you have 4 on x squared take 4, which is the left-hand side. So what we're looking for in a show that, all right, is this operation in between. Okay, so state what we start with, state what we finish with, and show that x take x cancels. All right, 2 take minus 2 becomes positive 4, and we have perfect square expansion on x squared take 2 squared, x squared take 4. Very good. Okay, now we have find the particular solution. Okay, so we're not finding, this particular solution means it's going through a particular point. So we have dy on dx, we have a differential equation here, equals 4y x squared take 4. Find the particular solution. Now, in part A, we've done a show that. Now, part B should read something like, hence find the particular solution. This is a hence, because anytime, you never do something randomly, okay? You don't do something for no reason. If you've shown that this is true, you're required to use this. So that means on the right-hand side, I can already see we've got that there except for the y. I'm going to keep that part on the right-hand side and pull the y over to the left-hand side. That's my first step. Okay? And we're going to integrate both sides with respect to x. And that term there, we don't have a formula to integrate that, so we're going to split it up into terms that we can. So we've got ln modulus of y. Let's integrate both sides with respect to x. Okay, we can't integrate that, so let's perform the substitution. The substitution is this. All right, we know 4 on x squared take 4 equals this. We've shown that it's true, so therefore we can substitute in here 1 on x take 2, take 1 on x plus 2. twice, maybe goes around the wrong way. 1 on x, no, that's correct. Okay, and then on the left-hand side here, we've got an integral of 1 on y with regards to y. Okay, so now let's process both of these. So the integral of 1 on y with regards to y is ln modulus of y. And on the right-hand side, we're going to have ln modulus of x take 2, take ln modulus of x plus 2 plus c. Now those two ln's, they can collect. We have ln of a take ln of b, ln of a on top of b. So we'll do that first. Now, when you apply e to a function, you're applying it to the whole side. So what that means, I'm going to really draw that out for you, is we have e to the ln modulus of y on the left-hand side. Yep, that's normal. And on the right-hand side is e to this whole power. All right, e to the ln modulus x take 2 on x plus 2, modulus plus c. All right, let's keep breaking that down. We'll have this left-hand side will simplify to modulus y. The right-hand side, let's split it up. Yep, let's split it up and then we'll simplify x take 2 on x plus 2. Okay, so using that, our first index law is split those into those two components. I'm going to apply the plus or minus to both sides. And e to the ln modulus of this side, well, that's just going to become x take 2 on top of x plus 2. And we've already considered the plus or minus, so we don't need to introduce another one. We're just stating it could be positive, it could be negative, depending on what these values come out to. All right. Now we can simplify that as well. So I might just come up here. Have enough room, plenty of room. Come up here. So we're going to let a equal plus or minus e to the c. Let's restate what we've got. X take 2 on x plus 2. Almost done. Find the particular solution given y of 0 equals 5. That means when x is 0, the y value is 5. So let's write that out and then communicate it. Substitute 5 where the y is, 0 where the x is. So 5 equals a times minus 1. A is minus 5. Therefore, the particular solution in this circumstance is minus 5, and then x take 2 on x plus 2. Y equals. A little bit untidy towards the end there. Okay, so the only extension part here, we did a substitution. That's the same up to here, but then we have a particular solution. A particular solution means it's going through a particular point. Use the information provided to determine the value of the unknown. Excellent. So that's separable differential equations, good fun skill. Yeah, let's get in.